Next, we'll develop the ideal diesel cycle. Now, a diesel engine also typically operates with piston-cylinder devices, and so we still have a compression ratio to concern ourselves with. However, in the spark ignition engine, the Otto cycle that we've just looked at, the fuel burns fairly rapidly. The spark initiates burning, the burning happens fairly quickly, and then is done. In a diesel engine, by contrast, the fuel is sprayed in over a longer period of time. So the fuel spray in and the burning occurs during expansion. We can't assume that the piston is just sitting still as the fuel burns, because the burn is simply not that rapid. So we're going to have to quantify how long the fuel is sprayed into the combustion chamber. To do that, we use the so-called cutoff ratio. Now, the cutoff ratio is given a similar symbol to the compression ratio, and it even sounds the same because both have a C word, right? Cutoff versus compression. But the cutoff ratio is different than the compression ratio. It has the same denominator, right? It's the minimum volume, or the volume at top dead center. But in the numerator is the volume of the system when the fuel spray is cut off. That's why it's called the cutoff volume, and therefore the cutoff ratio. So all this really does for us is help us quantify or put a number to the point when the fuel spray is cut off in the diesel engine. So the ideal diesel cycle actually looks a whole lot like the ideal Otto cycle, or the ideal spark ignition cycle. This is the ideal compression ignition cycle. You want to find it in your book as well. You'll want both the PV and the TS diagram. I recommend adding a tab to the page once you find them. I've included them in the slides, and you can see them there. There's the PV and the TS diagrams. And if you compare them to the Otto cycle, you'll notice they look very similar. Process from state 1 to 2 is the isentropic compression process. From 3 to 4, skipping 2 to 3 momentarily, from 3 to 4 is the isentropic expansion, or the power stroke. 4 to 1 is the constant volume heat rejection. So in a real diesel engine, of course, the piston cycles with the valves, the intake and exhaust valve, in order to get a fresh charge of air into the combustion chamber. Just like in the Otto or the spark ignition cycle. But what's different is the process from state 2 to state 3 is not a constant volume heat addition process. Instead, thermal energy is added by heat as the piston moves down, expanding. And so, in order to analyze this process, what we're going to have to do is make some assumptions. And one of the easiest assumptions to make is that somehow we're going to spray enough fuel into the combustion chamber so that the pressure in the chamber remains constant even though the piston is moving down. Is this perfect? No. Is it something that will help us at least get a little bit closer to the way that a diesel engine works versus the way that a spark ignition engine works? Yes. This will get us closer. So the only real change, if you notice, is that the process from state 2 to state 3, instead of being a vertical line on the PV diagram, as in the Otto cycle, now it's a horizontal line. It's a constant pressure instead of a constant volume process. So you'll notice on the TS diagram, the process from state to 2 to 3 is now labeled P equals constant, in other words, pressure is constant, instead of V equals constant, or in other words, constant volume. So if we look at the math behind the diesel cycle, we're going to play a lot of the same games we did before, where we have heat and work interactions that change the internal energy of the system. We haven't changed anything in the assumption that the air remains fixed in terms of the quantity of air. There's no mass that flows in or out. This is still a closed system. It's still a piston cylinder device with air, where the air is being heated up and cooled down and allowed to do work. And of course, work is done on the air as well during the compression process. Now, we can use an isentropic equation to represent the compression process. We can use an energy balance on the heat addition part, but this is different than the Otto cycle. What's different now is that as we're adding heat, the piston is moving down. That means the piston is doing work, right? So the gases are doing boundary work as heat is being added to the gas. And so we can't get rid of all of the work terms. We have heat in and boundary work out, and then the change in internal energy of the gas on the right-hand side. Now, if we move the boundary work to the other side of the equation, what you'll realize is that this is boundary work that is occurring at constant pressure. Of course, the whole reason for choosing constant pressure for this process in the cycle is so that the boundary work would occur at constant pressure and therefore can be added to the internal energy change and effectively be an enthalpy change. Now, let's not get confused here. The air above the piston does not have enthalpy, right? It is not a flowing fluid, therefore it does not have flow energy. However, because the boundary work occurs at constant pressure, mathematically we can add it together with the internal energy change and end up with the enthalpy change of the air being adequate for combining the energy change of the air itself as heat is added and boundary work is done, and the temperature change or the amount left over. So another way of saying this is that the heat that comes in is kind of like a deposit into a bank account. Some of the money stays in the bank account. That's the delta U, the change in internal energy of the air. Some of it leaves as a withdrawal, and that's the boundary work. However, because of the nature of the withdrawal, we can combine it with the internal energy change and just call it an enthalpy change. So we're accounting for the change in the internal energy of the air plus the boundary work withdrawal together in enthalpy. Now, of course, we can approximate delta H, the change in enthalpy between the two states, as Cp delta T instead of the constant volume heat capacity, because remember, constant pressure heat capacity goes with the enthalpy change. Again, we'll use an isentropic equation just as we did in the Otto cycle for the expansion process from state 3 to state 4, and then finally an energy balance from state 4 back to state 1. Remember, this is the process that represents the real engine going through 2 strokes in order to send the exhaust out and bring in a fresh charge of air. Now understand here, since the piston is not moving in the ideal cycle, right, because think about it, in the real cycle, what does the piston do? Well, it goes up, pushing the exhaust out, comes back down, pulling fresh air in. Well, we're just going to approximate that as the piston sitting still and the air losing heat, because that's the whole point of the exhaust and intake strokes. So again, as far as we're concerned, in the ideal cycle, the piston just sits down at bottom dead center, that's at maximum volume, and the air loses heat. Okay, so here are the equations from the previous slide. If we start putting things together as we did for the Otto cycle, we will begin with the thermal efficiency, trying to develop more insight into the thermal efficiency of the diesel cycle. So 1 minus Q out over Qn is still our go-to equation. We'll plug in Qn from the energy balance and Q out from the other energy balance. Once we do that, you'll notice that we end up with a CV over Cp. So unlike the spark ignition Otto cycle, you'll notice that CV over Cp won't cancel, but we can combine those two together into the ratio of heat capacities K, and that way it's just one term in the equation. Again, it's not obvious that we don't just plug in the 2 isentropic equations directly, but they do involve T1 and T2, T3 and T4, and if we work them in via algebra, what you'll end up with is an equation that looks like this for the thermal efficiency of the diesel cycle. Now, part of this should look familiar, but there's also a new piece here. This second term that's in square brackets is new. Other than that, the thermal efficiency looks exactly like the thermal efficiency of the Otto cycle. Now you'll notice that in this term we've got the cutoff ratio. Be careful, it's not the compression ratio. You see that subscript C and your mind automatically thinks compression ratio because you're used to that. But it's not that, it's the cutoff ratio. Remember, this is the volume when the fuel spray is cut off over the minimum volume in the stroke. And you'll notice that the ratio of heat capacities appears there in the denominator as well. Again, it's not obvious to see this, but this particular term is always greater than 1. Now, what does that mean? Well, what that means is that this factor is always multiplying by the term that is taking efficiency away from 100%. You can look at it that way. Think about it. The efficiency would be 100% if it weren't for all of these other pieces, right, that have the minus sign on them. So the lower the compression ratio, the bigger the amount that's being taken away from 100% efficiency, and the cutoff ratio, that term being greater than 1, always amplifies the negative term and takes more away from 100% efficiency. What does this mean? This means that theoretically the efficiency of a gasoline engine should be more than the efficiency of a diesel engine. You might look at that and say, well, wait a second. Now I realize that all this stuff we're learning is just garbage because I know that diesels have a reputation for being more efficient than gasoline engines. There are a couple reasons for that. Normally when we think about the efficiency of an engine, we think about it in terms of miles per gallon because we know we want to get miles out of it, we know we have to put gallons into it. But as we've already seen, that's not necessarily the best metric because it's not dimensionless, right? There's problems that can enter into that analysis. For example, when you buy a gallon of diesel, you're actually buying more energy than when you buy a gallon of gasoline. There's literally more energy in the diesel than there is in the gasoline. Now, it's not a huge difference, but it is some. And that's part of the place where we get the idea that diesel engines are more efficient than gasoline engines. And in fact, they actually are. Now, why is the theoretical efficiency backwards of what we experience in real life? Well, we have to really study this thermal efficiency equation to understand it. The cutoff ratio causing the second term to increase is not the only factor. There's still the compression ratio to consider, and since we bring in air without any fuel into the combustion chamber and then compress it, we can compress it as much as we like as long as the engine doesn't blow apart, right? So why not compress the heck out of it, get a high compression ratio, which we have to do anyway, because when we spray in the diesel, we want it to start burning. We don't have a spark ignition to make that happen, so the air has to be at a high enough temperature to cause the diesel to burn. And since we can control the rate at which fuel is sprayed in, we can prevent the engine from knocking so badly. Now, you might notice that diesel engines actually are more noisy. They do sort of knock if you listen to them. And that's because the fuel is burning pretty much instantaneously as it goes into the combustion chamber. So if you look at the typical compression ratios that diesel engines use, they're much higher than what spark ignition or gasoline engines use. And typically anywhere from 12 to 23 is a good range for the compression ratios for diesel engines. Now, if you think about it, if you set the cutoff ratio to 1, it turns out that second term in square brackets will be equal to 1. It'll just kind of go away out of the equation, right? And you're back to the efficiency of the Otto cycle. And so if you look at the curves here, you'll notice that the highest efficiency curve is the curve for the Otto cycle, where the cutoff ratio is equal to 1. But as you increase the cutoff ratio, the efficiency curve decreases because, of course, we're taking more and more from 100% efficiency in that square bracketed term. Now, since the diesel engines have such higher compression ratios, we still end up with efficiencies that are greater in a diesel engine versus a gasoline engine.